Hey, if you are new here, this is Chandan and you are watching the learning video. Okay, so in this video we are going to discuss about the questions from the linear algebra of CSIR NET 2022 February section, and in this video we are going to discuss the questions of part B. Okay, that is the questions of 3 marks. Okay, and in the questions paper of 2022 there are total 6 questions of 3 marks from linear algebra and 7 questions from linear algebra from 4.75 marks. Okay, so in this video we are going to discuss about these 6 questions which are of 3 marks. Okay, each of 3 marks, and this means there are total 18 marks in part B. Okay, in this question paper. Okay, so let's start, and before starting the solution I am requesting you to all those who are new in my channel, please like the video, comment if you have any doubt in the comment section below, and don't forget to subscribe the channel. Okay, so the question 1 is the question says that consider two statements given below. There exists a matrix n belongs to M4R such that 1 1 1 minus 1 and 1 minus 1 1 1 is a basis of row of n, and 1 2 1 4 belongs to the null space of n. Okay, that means the vectors 1 1 1 minus 1 and 1 minus 1 1 1, whether this is a basis, if there exists a basis, this one is the basis, is the basis of row space, that is these vectors are the row vectors. Okay, and 1 2 1 4 it belongs to null n. That means if we take a system such that Ax equal to b, then this Ax is such that if we put this X at the values at X, okay, so that gives Ax equal to 0. Okay, so that means whether the vector for a linear transformation M, for this vector this transformation goes to what, 0. Okay, so this is the case. So we first discuss this one, and the second statement says that there exists a matrix M belongs to R such that this is a basis of column space of M, and 1 1 1 1 transpose and 1 0 1 0 transpose belongs to null M. Okay, so and here 4 statements are given. Okay, so let the solution is, let 1 1, this is the basis of row vector of n. Okay, that means these two vectors are row vectors, and these two vectors, suppose we let the two vectors, another two row vectors, this one a31 a32 33 and so on, and this is the column vector. Okay, so this is the vector for which this belongs to what, null space. That means if we multiply this by this vector this, then this must be equal to 0, but we see here that there is a non-zero term. Okay, we don't need to know these two terms, because one terms in the matrix is non-zero, means the matrix is non-zero, that is a matrix is not 0 0 0 0. Okay, so that means the vector 1 2 1 4, this one is not belongs to the column space. That means option 1 is false. Okay, so since option 1 is false, therefore we can discard the options D. It says that both statements 1 and 2 are true, and 1 is true, 2 and false, so we can discard the options B and D. So now we comes to the next. Let T be the linear transformation. Okay, so MT is the linear matrix of T. Since these two vectors is a basis, is the given in the second option. Okay, 1 1 1 0, and these are the columns vector. Okay, see here is the transpose. Okay, that means these are the column vectors. Okay, basis of column M. Okay, that means they are linearly independent, obviously, so they belongs to the range space of MT. Since these are the column vectors, therefore the vector must belongs to the range space of the matrix of the linear transformation T. Okay, so and there exist two vectors alpha and beta such that, oh, since these two vectors belongs to the range space, that means there are another two vectors alpha and beta such that T of alpha equal to this vector, since this is the range vector in the range space, and T of alpha, this is T of beta, this is equal to this vector. Suppose we take latent alpha and beta. Okay, and T alpha and T beta linearly independent vector, therefore alpha and beta must be linearly independent. Okay, so take the vectors alpha equal to 1 0 0 0 and beta equal to 0 1 0 0, that is this is E1 and this is E1, we easily say that. Okay, so these two vectors are linearly independent. That means since these two vectors are linearly independent, therefore these vectors and these vectors belongs to nullity of M. Okay, so this means T1 1 1 1 equal to 0 0 0 and T1 0 1 0 is equal to 0 0 0 0. Therefore matrix of T is exist, and matrix of T equal to this one. Okay, 1 0 0 0. Suppose let us take the vectors alpha first, then these vectors beta, and then these vectors 1 0 1 0, the given vectors, and then these given vectors. Okay, so see whether these vectors are linearly independent or not. Okay, so this matrix is clearly a upper triangular matrix. Okay, therefore the determinant of the matrix is the product of the diagonal elements, that is 1 1 1 1, this is equal to 1. Okay, so since determinant equal to non-zero, therefore the vectors of the matrix must be, the vectors in this matrix must be linearly independent. Okay, so here this is follows that the vectors are linearly independent. Okay, so security what this date is non-zero, therefore the vectors are linearly independent, therefore 2 option is true. Okay, so here option 1 is false and 2 is true. Okay, so C is false option and A is our correct option. Okay, now go to the next question. Next question, let A and B be two n by n matrix. Suppose that the sum of the elements of any row of A is 2 and the sum of the elements in any column is of B is 2. Which of the following matrices are necessarily singular? Okay, so there are given two conditions. Okay, sum of the elements in any row in A is 2. Okay, and sum of the elements in any column in B is 2. Therefore, if we take any matrix A and B which satisfies these given conditions, okay, and then we just apply the take the matrix and put these forms to check whether they are singular matrix or not. Okay, that is the determinant of the matrix, this one, or the 4 options are 0 or not. Okay, so we first choose, but and here one thing also noted that this n is not given, that is if we take any form of m, that is any value of m, the remaining must be wholes. Okay, so let us first choose n equal to 2 for our calculation is to be easy. Okay, choose A equal to this one 1 1 2 0, that is the row sum is 2, the row sum is 2, and B equal to 2 0 1 1. I take this matrix, same matrix, just changing the transpose, or you can say it, you can see it easily. Okay, so this column sum is 2. Okay, so first we check whether I minus half of B A transpose is equal to singular or not. Okay, so half I minus half of B A transpose, we just calculate it here, you can just calculate, and we get minus half minus 2 minus half minus 1. Okay, and this determinant is non-zero. Okay, so that means A is singular, the matrix in the given option is singular, this is false option. Okay, now go to the next one and check, and the second option is given I minus half into AB. Okay, so I minus half into AB, this gives this one, which is also non-zero matrix, that is the determinant of this matrix is non-zero, that means option B is also a false option. Okay, this is false, this is false, that is option B is false. Now we just calculate AB multiplication and BA transpose multiplication, therefore the options calculation for C and D is again very easy. Okay, so C equal to I minus 1 by 4 AB, this is equal to this matrix, and that of this is not equal to 0, that means option C is also false option. Okay, option C is also false, so option C is also false, and option D clearly the true option. And you can check, okay, for your so this is equal to D equal to I minus 1 by 4 B A transpose, which is equal to this one, and the determinant is equal to 0, that is the matrix of in option D is singular. Okay, so D is true here. Now go to the next question. Let A be the 4 by 4 matrix such that these are the eigenvalues of A and B equal to this one, then the trace of AB is equal to, okay, so we have to first find the eigenvalues of B, and here we know that, what we know that if lambda is an eigenvalue of A, then lambda power n is an eigenvalue of A power n. Okay, so we use the result here. Okay, so lambda 1, suppose lambda 1 of A equal to minus 1 1, lambda 2, lambda 3 equal to 1, and lambda 4 equal to minus 2. Therefore trace of the matrix A equal to sum of eigenvalues, trace equal to, you all know that, sum of eigenvalues. Okay, now we first find the eigenvalues, 4 eigenvalues of B. Okay, so the 4 first eigenvalues of B with respect to the eigenvalues minus 1 of A, this is equal to minus 1 to the power 4, since minus 1 is an eigenvalue of a, therefore minus 1 to the power 4 is an eigenvalue of a to the power 4. Similarly, we can calculate the remaining. Okay, so we get the first eigenvalue 1, similarly the second eigenvalue 1, third eigenvalue 1, and fourth eigenvalue is also 1. Okay, so the trace of b equal to 4. Okay, now we have to calculate the values trace of ab. Okay, so trace of a plus b equal to trace a plus trace b, which is equal to minus 1. This is the trace of a matrix, and 4, this is the trace of b matrix. That we get the option 3 C, and option is 3. The trace of a plus b is equal to 3. Okay, so here option C is correct. Now go to the next one. Next question, question number 4 of part B, says that let m equal to this matrix. Given that 1 is an eigenvalue of m, then what? Then the question says that which of the following statement is are true. Okay, so minus 2 is an eigenvalue of m. So we first calculate the eigenvalues. Okay, since here given that 1 is an eigenvalue, and here note that the column sum of all the columns is equal to 2. Okay, see, and we know that if the row sum or column sum of a matrix is same for all column or for all row, then the sum is an eigenvalue. Okay, so here so 2 is an eigenvalue. Okay, so we get two eigenvalues, 1 and 2. Okay, and now from the result that lambda be the third eigenvalue of a, therefore sum of eigenvalues, this is equal to trace. Okay, so this gives 2, therefore the eigenvalues are 1, 2 and 2. Okay, so the eigenvalues are 1, 2 and 2. Therefore option A and B says that minus 2 is an eigenvalue. No, this is false. And 3 is an eigenvalue. This is also false. Okay, and now we check the option C and D whether the eigenspace of the each eigenvalue has I dimension 1. That means what? That means we have to calculate for gm for each lambda I whether this is equal to 1 or not, the C option, since geometric multiplicity gives the dimension of the eigenspace. Okay, so we check whether this is 1 or not, and then option D. Okay, so geometric multiplicity gives the dimension of the eigenspace corresponding to each eigenvalue. Therefore gm of 2 is equal to eta of m minus 2i. Okay, so 3 minus gm means what? Rank of this matrix. 3 is the order of the matrix minus rank of m minus 2i. Okay, since 1 is eigenvalue and algebraic multiplicity of 1 m of 1, this is equal to 1, therefore gm is also equal to 1. Okay, since m greater or equal to gm, therefore we can easily say that m and gm in this case is equal. Okay, so then we just calculate the case for the eigenvalue of lambda equal to 2 here. Okay, so for lambda equal to 2, m minus 2i gives this matrix, and rank determinant of this is equal to 0. Okay, so determinant 0, that means rank of this matrix m minus 2i is less than 3. Now if we get a submatrix, square submatrix of order 2, then we can say that the rank of the matrix is equal to 2. Therefore here we can get a submatrix of order 2 by 2, that means rank of the matrix is equal to 2. Okay, this is a non-zero submatrix, and therefore rank of 2 equal to 2. You can here also apply row operation to check the rank. Okay, now therefore rank of this equal to 2, that means gm of 2 equal to 3 minus 2, since 3 is the order of the matrix and 2 is the rank of m minus 2i. Okay, so this is equal to 1, that means C is true. That means the dimension of eigenspace corresponding to each eigenvalue is equal to 1. Okay, so this is our correct answer, and we don't have to check whether this is diagonal as well or not. If you are interested, then you can check also. Option D is incorrect. Now go to the fifth question. Let n greater than 1 be a fixed natural number. Which of the following is an inner product on the vector space of n by n real symmetric matrix? Okay, so this is a very easy question. Okay, so the question option is the given, so you just need to know the definition of the word of the inner product space. Okay, so let B equal to mn for the case matrix here. Okay, since the question is based on the matrix, therefore we have just calculate, or we have just applied the definition of the inner product space in case of matrix. Okay, so over A, and define the inner product as AB equal to trace of B transpose B. This is theta A, that means this is the general definition for complex field. Okay, so if B is an inner product space with the given inner product, above defined inner product is standard inner product on V. Okay, now if F equal to R, therefore the inner product of AB, this is equal to trace of B transpose A, okay, for real matrix, okay, and this is the general definition for complex field or complex matrix, okay. So given AB a real symmetric matrix, therefore A transpose equal to A and B transpose equal to B, okay. Now the inner product is AB equal to trace of B transpose A, and since B transpose equal to B, therefore trace of we put the B transpose equal to B, which is equal to trace of BA, and we know that the properties of trace, that is trace of AB equal to trace of B, that means this is equal to clearly trace of AB, okay. Therefore which option? Trace of AB. Clearly option B is correct, okay. This is very easy question. Now the question number 6 from part B, and this is the last question of part B, that is from 3 marks, okay. So let B be a M3/3 matrix over the field R, A transpose plus A belongs to R into I, okay. So this is R product I means the identity matrix of order 3, where I is the identity matrix. Consider the quadratic form defined as Q of A equal to trace of A square minus trace of A whole square. Trace of A square means here the QA is defined as trace of A whole square minus trace of A square, okay. So this is the defined, the given defined quadratic form, okay. So here there are no condition given on A, okay. Therefore we just consider the matrix A with a general form, okay, this one. Therefore A transpose equal to this one, A plus A transpose belongs to Ri, okay. So for any real number K, the matrix A plus A transpose seeing as K into I, okay. So therefore A plus A transpose equal to this matrix, which is equal to this matrix, since K into I means K in the diagonal and the remaining term are terms of 0, okay. So now comparing both sides, we get this term equal to K, this term equal to 0, therefore we get A11, A22, A33 equal to K by 2, A12 equal to A minus 21, this one, that is, this is clearly a skew symmetric matrix, I think, yes. So this is the given, this is the defined the latest A, okay. By applying the conditions in the given in the questions, we get the form of the matrix A is equal to this, okay. So that is A takes the form this one, okay. So now trace of A equal to sum of the diagonal elements, you can say this is equal to 3k by 2, and therefore trace of A whole square, this is equal to 9k square by 4, okay. Now we find the trace of A square, okay. So we just take A square, so A square equal to this, and here we just calculate the diagonal terms. Why? Since we just need to calculate the trace, therefore we don't have to calculate the remaining terms, okay. This is the work done for this case is very big, okay, so that we don't have to calculate these terms, okay. So this is the diagonal terms, and this one, the term is just matrix multiplication k square by 4 and remaining these terms, okay. That is trace of A square, this is equal to this one, the sums only, okay. So this gives 3k square by 4 minus this, okay. Now Q of A, that is quadratic form of A, is equal to trace of A square minus trace of A square, okay. Trace of A square means this one, and trace of A whole square is this one, and trace of A square means this one. So we get 6k square by 4, and this is the given quadratic form. Now we know that the quadratic form is written as in the form of what? This is QA, this is equal to X transpose X, where X equal to these vectors are X, okay. You just remind this thing to write the form of to write the quadratic form, okay. Just write the matrix as it is here, and then the transpose in the right side, and then you have just put the values of these, okay. So k square means 6 by 4, k 6 by 4 into k, that means k square. If we multiply these three matrices, then we get this term, okay. This is the form to write the what? Quadratic form, okay. So these are the coefficient, we just write it here, okay. So since this is a diagonal matrix and all the diagonal elements are greater than 0, and we know that for a diagonal matrix the eigenvalues are the diagonal elements, okay. So these are the diagonal elements and these are the eigenvalues, and all the eigenvalues are greater than 0, okay. So therefore the signature is this, all eigenvalues are plus, okay. So this is, oh, I just forget to write the options, okay. Here the options like that signature. Just a minute, I just forget to write the options. Okay, I just forget the right options. Okay, so options like that. Okay, I just remind signature is what, plus 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 and plus minus plus s. Okay, so you just check out the options. Okay, sorry for that, I forget that. Okay, so this is the last question and the answer is this one. Okay, so this is the questions from part B up to part B, total 6 questions. Okay, so if you like the content, then please give a like. If you like the content, then please give a like to this video, share with your friends and subscribe the channel. Okay, so next meet in the next video. Okay, thank you, see you again in the next video. Okay, thank you.